Imagine a computer chip that doesn't just process data, but learns from it. A chip that adapts to new information like we do, becoming smarter over time. Imagine robots that can learn from human interaction, healthcare devices that can recognize patterns in our bodies like a doctor, or even an AI system that can predict and avoid traffic jams in real time. Today, we're going beyond bits and bytes. We're diving into the world of neuromorphic computing, where computers are designed to think more like us. It is a frontier that promises to revolutionize everything from the way we drive our cars to how we understand the human brain itself. So let's dive right in and explore the cutting edge of this exciting field. What if the key to the next generation of artificial intelligence lies not in more processing power, but in a different way of thinking? Enter neuromorphic computing, a revolutionary approach that takes inspiration from the most complex machine in the known universe, the human brain. Unlike conventional von Neumann architecture, which has dominated computing for decades, neuromorphic computing reimagines how data is processed and stored. Just like our brains use neurons and synapses, neuromorphic systems use artificial neurons and synapses. This approach mimics the way our brains adapt and learn by changing the strength of connections between neurons, allowing the system to improve its performance over time. But why the brain? Why not just stick with what's worked for so long? Well, because the brain is incredibly efficient. It can perform complex tasks using far less power than today's computers. And it's highly adaptable, capable of learning new things throughout life. In contrast, current computers struggle with tasks that seem effortless to us, like recognizing faces or understanding natural language. They also consume massive amounts of energy, which raises both financial and environmental concerns. Neuromorphic computing offers a solution by providing a new paradigm for processing information inspired by the very essence of human intelligence. It's like turning the computer inside out, putting the memory and processing power back together in a way that mirrors the complexity and efficiency of the human mind. Today, neuromorphic computing is more than just a futuristic concept. It's a rapidly developing field with major players like Intel, IBM, and Samsung investing heavily in research and development. For instance, Intel has developed a neuromorphic chip called Loy, which uses 1,000 times less power than a typical processor while offering high performance in real time. IBM, on the other hand, has created a chip called TrueNerve that mimics the human brain by using interconnected networks of artificial neurons. These advancements are not just about creating smarter machines. They're about solving real-world problems in a more efficient and effective way. For example, neuromorphic chips could be used to develop advanced robotic systems that can navigate and interact with the world around them in a more intuitive way. Imagine a robot that could learn from human interaction rather than being programmed to follow a set of rigid instructions. Or picture healthcare devices that can analyze a patient's vital signs and predict potential health issues before they become critical. The applications are truly endless. Even traffic management could be transformed with AI systems that can anticipate and avoid gridlock, making our commutes smoother and more efficient. The potential benefits of neuromorphic computing are vast, spanning across industries and aspects of our daily lives. As this technology continues to evolve, we can expect to see more innovative applications that were previously unimaginable. At the heart of these neuromorphic chips are artificial neurons and synapses. Artificial neurons, or neurons for short, are the basic building blocks of these new computer systems. Much like their biological counterparts, they receive, process, and transmit information. When activated by input signals, they perform a calculation and pass the result to other neurons, allowing data to flow and be processed. Synapses, on the other hand, are the connections between these neurons. They play a crucial role in determining how efficiently and effectively information is transmitted. The strength of these connections can change based on the patterns of activity, a process that mirrors the way our brains form and strengthen connections between neurons through repeated use. This adaptability enables neuromorphic systems to learn and improve over time. By adjusting the strength of connections between artificial neurons, these systems can adapt to new information, much like we do. This mimics the biological process of neuroplasticity, where our brains physically change in response to learning new things or adapting to new situations. One of the key advantages of using spikes to represent data is their temporal nature. Unlike the static values used in traditional computing, spikes have a time component. They occur at specific moments, and their precise timing carries information. This temporal aspect closely resembles how our brains process information, taking into account not just the information itself, but also when it arrives. This temporal representation allows for more nuanced and context-aware processing, similar to the way our brains handle language, recognizing that the meaning of a sentence can change based on the intonation and pauses in speech. Additionally, the asynchronous nature of spiking neurons reduces the need for a global clock, a component that is not only expensive in terms of energy consumption, but also introduces synchronization issues. This inherent temporal structure mirrors the way our brains process information, making it an efficient and effective way to represent data. Furthermore, this approach aligns well with the asynchronous operation of biological neurons, which communicate using spikes that occur at varying times. By adopting this approach, neuromorphic systems become more akin to the human brain in their operation, potentially leading to more accurate and efficient processing of information. Now let's talk about the difference between neuromorphic chips and traditional CPUs and GPUs. First off, let's talk about von Neumann architecture. This is what we've been using for decades, and it is basically the standard architecture for most computers. The data and the instructions to process that data are stored in the same place. So the CPU fetches both the data and instructions from the memory, processes them, and then writes the results back to the memory. But this has some limitations. Fetching and storing both data and instructions in the same place can cause bottlenecks. Imagine a chef in a kitchen trying to cook from a cookbook while also doing the dishes. That's basically what's happening here. The chef has to keep returning to the same spot for more instructions and data. It works, but it's not the most efficient way to operate. On the other hand, we have the Harvard architecture. This architecture separates the data and instructions, kind of like separating the chef and the cookbook. The data stays in one place and the instructions to process the data stay in another. This separation allows the computer to fetch instructions and data simultaneously, leading to faster processing. Now, this is where neuromorphic chips come in. They take this concept further. Instead of having separate locations for data and instructions, they embed the instructions directly into the chip. This eliminates the need to fetch instructions, reducing power consumption. And instead of using binary code, 0 south and 1 south, they use spikes, a more biologically inspired way of representing data. Think of it as the chef getting the recipe written on a tablet directly and only needing to look at the instructions for each step, not the whole cookbook. This way, the chef can focus on cooking without getting distracted by all the other recipes in the cookbook. The spike-based approach not only aligns better with the way the human brain operates, but also offers an energy-efficient alternative to traditional computing. This shift from von Neumann to Harvard and finally to the embedded instruction approach represents a significant leap forward in computing efficiency. Each step moves us closer to a system that operates more like the human brain, which is incredibly efficient and adaptable. It's undeniable that neuromorphic computing is poised to disrupt the AI landscape. Its potential impact is nothing short of revolutionary. One of the most significant ways in which neuromorphic computing is set to disrupt the AI landscape is by enabling faster decision-making. Unlike traditional computers that rely on algorithms and predefined rules, neuromorphic systems can mimic the human brain's ability to learn and adapt. This means they can make decisions quickly and efficiently, even in situations they've never encountered before. For example, in healthcare, these systems could analyze a patient's symptoms and recommend a course of action in real time, potentially saving lives. Similarly, in autonomous systems, they could react to unexpected events on the road and make split-second decisions that could mean the difference between safety and disaster. However, it's important to remember that while neuromorphic computing offers many advantages, it's not a silver bullet. There are still challenges to overcome. For instance, designing algorithms that can take full advantage of the unique capabilities of neuromorphic systems will require new approaches. Moreover, integrating these systems with existing technologies will also pose challenges that need to be addressed. Despite these hurdles, the potential benefits are too great to ignore. The prospect of machines that can learn, adapt, and make decisions like humans is not just a futuristic fantasy. It's a real possibility that neuromorphic computing is bringing within reach. As this technology continues to evolve, we can expect to see more applications that leverage its unique capabilities, transforming industries and improving our lives in ways we're only beginning to imagine. So what does the future hold for neuromorphic AI? Well, as research progresses and these systems become more sophisticated, we might see them handling tasks that are currently considered too complex for computers. This could range from advanced robotics that can navigate and interact with the environment in a human-like manner to personalized healthcare solutions that can tailor treatments to an individual's specific needs. Furthermore, neuromorphic AI could play a pivotal role in understanding the human brain. By developing computer models that mimic the brain's structure and function, researchers can gain valuable insights into how the brain works, which could lead to breakthroughs in treating neurological disorders. However, it's important to consider the ethical implications of developing AI that thinks more like a human. Questions about consciousness, sentience, and control will need to be carefully considered as this technology advances. Nevertheless, the potential benefits of neuromorphic AI are vast and could revolutionize various aspects of our lives. From healthcare to robotics and beyond, the future of neuromorphic AI is filled with possibilities that promise to blur the line between man and machine. As we continue to explore this fascinating field, one thing is clear: we are only at the beginning of a journey that could lead to a future where machines not only think like us, but also learn and adapt in ways we've only dreamed of. Now let me ask you, what do you think? Will neuromorphic AI lead to true artificial general intelligence? And what do you think are the biggest challenges and opportunities in this field? Let us know your thoughts in the comments below. Don't forget to like this video if you enjoyed it, subscribe for more updates. And thanks for joining me on this journey through the world of tomorrow. Until next time, keep thinking critically, keep asking questions, and keep pushing the boundaries of what's possible.